Hello and welcome to the web series ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
Okay. Hello, I'm Athanasios Stasinakis. I'm professor at the University of the Aegean in Lesbos Island in Greece, and I'm going to present you some results concerning the construction and the operation of the pilot system that was constructed under the frame of ZeroPM project. Just a brief information about the structure of the presentation. In few slides, we will see about the PFAS occurrence in sewage sludge and about their fate during sludge treatment. And afterwards, I will provide you some information about the construction, the operation, the performance of the system. Also, some results from our lab experiments regarding the treatment of the hydrochar liquid, and at the last slide, the main findings and some future challenges. So, I think that more or less it is well known to all of us that a great amount of PFAS are found in municipal wastewater. We also know that these compounds cannot be biotransformed during the activated sludge process, but an important amount of them it is sorbed to the total suspended solids and also to the activated sludge flocks that we have in the bioreactors. As a result, PFAS are accumulated to primary and secondary sludge, and as a result, they can be found in sewage sludge. Before 10 years, we wrote a review article and we saw that the number of PFAS that had been detected in sludge in 2015 was 19 compounds, and their concentrations were in the range of few nanogram per gram to some 100 nanogram per gram. 10 years later, the number of PFAS has been increased to almost 180, and we can find information about PFAS precursors and also for ultrasound and new generation PFAS. The highest concentrations are still found for PFOS, PFDS, and PFOA, and at the moment there are available analytical methods that can analyze simultaneously more than 20, 30, or even 40 PFAS. As regards their removal during conventional sewage sludge treatment, I have to say that in most of the sewage treatment plants around Europe, the processes that are applied are thickening, anaerobic digestion, dewatering, and in some cases solar or thermal drying. In the anaerobic digestion, where we have anaerobic bacteria in closed reactors at elevated temperature of 35 degrees of Celsius, there are some studies that show that actually PFAS cannot, most of the PFAS cannot be biotransformed. In some cases, we have also some contradictory results. For example, there are some studies in full-scale systems saying that a moderate decrease of the sum of PFAS can be achieved. In other cases, it is reported an increase of the total PFAS mass as after anaerobic digestion. It has also been observed an increase on the concentration of specific PFAS. So, in general, I could say that according to the published results, a small or no removal of PFAS is expected during a conventional anaerobic digestion process. On the other hand, there are some papers and some results from lab scale experiments or from pilot scale experiments. In these papers, they have applied thermal technologies such as incineration or pyrolysis, and the authors provide data showing that a quite high removal of PFAS, several PFAS, can be achieved in these cases. So, based on these results, the idea of the ZeroPM was to test some novel technologies, and we focused to hydrothermal carbonization process, which is a thermal process where we apply temperature of around 250 degrees of Celsius and high pressure in the reactor. We would like also to modify some of the existing processes, such as the anaerobic digestion, and we also like to combine different technologies in series. Based on this idea, we conducted for the first 2 years of the project experiments in the lab in order to see which is the fate of the PFAS during thermophilic or mesophilic anaerobic digestion, what is happening when conductive materials such as granular activated carbon is added in the bioreactor, or when we apply voltage. In parallel, we conduct lab experiments with hydrothermal carbonization reactor in order to see which is the role of pressure, of temperature, and the pH on the removal of these compounds. After publishing these results, we proceed with the design and the construction of the pilot system. The system operated for 2 years, and it combined different technologies in series. So as a first step, we had the pre-treatment of sludge, and we checked 2 different pre-treatment processes, thermal pre-treatment and ultrasound pre-treatment. Afterwards, the pre-treated sludge was transferred to an aerobic digester, and as a last step, we had a hydrothermal carbonization reactor. The system was installed in the wastewater treatment plant of Mytilene in Lesbos Island, and some information about the construction of the system. The volume of the thermal pretreatment reactors was 30 liters. We used an ultrasound sonicator with a maximum output power of 1000 watt and an operating frequency of 20 kilohertz. The volume of the anaerobic digester was 500 liters. It was a continuously steered tank reactor heated by a boiler and equipped with an agitator. For the hydrothermal carbonization reactor, we supplied an instrument from PAR, and its volume was 8 liters. And we used also a SCADA system in order to remote control the key process parameter and to collect data from the operation of the system. Some of the parameters were monitored continuously. In order also to record the energy consumption, a 3-phase energy meter had been installed in the system. The experimental methodology that was applied, the startup of the anaerobic digestion was achieved using anaerobic sludge from a UASB reactor that had been constructed and operated in the island. During the whole experiments, we used as feeding secondary sewage sludge at a flow rate of 28 liters per day. We operated the anaerobic digester at the mesophilic range and at an hydraulic retention time of 18 days. The first phase for the operation of the anaerobic digester was an acclimatization phase, and afterwards we conducted experiments in 5 different experimental phases. In phase A, we examined the operation of anaerobic digestion in conventional mode coupled with hydrothermal carbonization reactor. In phase B, we examined the treatment of the sludge applying thermal pretreatment at a degree of 80 degrees of Celsius and for 1 hour. And after thermal pretreatment, we use the anaerobic digestion and the hydrothermal carbonization reactor. In phase C, instead of thermal pretreatment, we used ultrasound pretreatment. In phase D, we operated the anaerobic digester after adding granular activated carbon as conductive material in a concentration of 10 grams per liter. And in phase E, additionally to the GAC, we applied also electric potential at a voltage of 2 volt. The parameters that were monitored during the study, we took samples from the influent and effluent of each reactor, and we analyzed them for all the conventional parameters that are usually monitored during the operation of anaerobic digestion. For example, total solids, volatile solids, total and soluble COD, BOD, ammonium, nitrogen, phosphorus in the form of orthophosphates, volatile fatty acids. We also monitor the production of biogas and the composition of biogas. At the end of each phase, we collected biomass from the anaerobic digester and we characterized it. And regarding the concentration of PFAS, we collected samples in consecutive days at the end of each phase from the influent and the effluent of each reactor, and we analyzed them in the dissolved and in the particulate phase. The method that was available could analyze 29 PFAS, so we developed and optimized the method for 4 different matrices, for the hydrochar and also for the sludge, and we apply SPE, solid phase extraction, for the liquid part, and liquid extraction for the solid part, and we analyze them in LCMSMS. Now some results about the performance of the system. At first, I have to say that we showed an increased biogas production in the anaerobic digester after sludge pretreatment, either thermal pretreatment or ultrasound pretreatment. It is known in the literature that these processes enhance the hydrolysis of the organic matter and result to the increase of the soluble COD in the bioreactor. We also showed an increase on the biogas production after GAC addition, probably due to the promoted direct interspecies electron transfer phenomenon, and also after the application of voltage, probably due to the accelerated hydrolysis and acidogenesis. In the anaerobic digester, we also noticed elevated concentration of ammonium nitrogen because part of the organic nitrogen is converted to ammonium nitrogen through ammonification, and we also saw elevated concentration of ammonium nitrogen after hydrothermal carbonization because part of the organic nitrogen is released in the dissolved phase. Something which was also interesting was the characteristics of the liquid that is produced after the hydrothermal carbonization. Its pH is almost neutral, but it is heavily contaminated with COD and ammonium nitrogen, and also in this liquid we detected some PFAS, around 6 to 7 compounds, if I remember well, at quite low concentrations. The highest concentration was for PFBS, and it was around 10 nanogram per liter. Now, as regards the operation of the system and the detection of PFAS, in the sludge, in the raw sludge that we used in our experiments, we detect 25 out of 27 PFAS. 6 of these compounds had a total, as total was the sum of the dissolved and particulate concentration, and this concentration was higher than 100 nanogram per liter. The highest total concentration was found for 6 to 2 FTS and also for PFDA and PFOS. In parallel, most of the target compounds were found in the particulate phase, but of course there were differences on their distribution according to the target compound and its chemical property. During the pre-treatment processes that were applied and during the anaerobic digestion, with the conventional anaerobic digestion, we did not see any removal of PFAS, but after a pre-treatment there was changes in the distribution of some compounds, specifically the concentration of these compounds in the dissolved fraction increased. As I said before, during conventional anaerobic digestion, there was no removal of PFAS based on the mass balance that we applied. On the other hand, when we added GAC or voltage, we saw that for some PFAS there was a partial removal. As regards the hydrothermal carbonization, the operation of the reactor at a temperature of 250 degrees of Celsius and a pressure of 36 bars for 2 hours achieved important overall PFAS removal. 13 compounds were removed by a percentage higher than 80%, while the highest removal was observed for perfluoroalkyl sulfonamides, whereas the removal of perfluoroalkyl carboxylic acids and perfluoroalkyl sulfonic acids range between 40 to 100%. As regards energy consumption of the system, if we exclude the use of the hydrothermal carbonization reactor, the energy consumption ranged between 8.3 to 19 kilowatt hours per day, depending on the temperature of the environment and the pretreatment process that applied in each phase. And when we calculated the energy consumption per cubic meter of treated sewage sludge, we saw that thermal pretreatment needed 160 kilowatt hours per cubic meter, the ultrasound pretreatment 64 kilowatt hours per cubic meter, the anaerobic reactor between 186 and 482 kilowatt hours per cubic meter, and the hydrothermal reactor 125 kilowatt hours per cubic meter. At the last part of our study, we conducted also some lab experiments for the liquid treatment of for the treatment of the liquid that is produced after hydrothermal carbonization. In these experiments, we try to treat this heavily contaminated liquid in a reactor that was an aerobic moving bed membrane bioreactor. With a hydraulic retention time of 24 hours and a solids retention time of 20 hours. And we conduct experiments in 3 experimental phases. In phase 1, we diluted this liquid with municipal wastewater at a ratio of 10%. In phase B, we applied as pretreatment process struvite precipitation in order to remove the major part of ammonium nitrogen that is found in HTC liquid. And in the phase C, again, we apply struvite precipitation and we diluted the supernatant with municipal wastewater in the percentage of 20% supernatant and 80% municipal wastewater. And we also added in this in the bioreactor PAC, powdered activated carbon, in order to see whether we could have a higher removal of the conventional pollutants and also removal of PFAS in the presence of PAC. At the end, we did also some experiments with nanofiltration in order to see if we can achieve a further removal of PFAS after the use of the membrane bioreactor. At the biological treatment, we saw that for PFBS was not removed during biological treatment in any of the experimental phases, and it was shown that actually it couldn't also be removed due to sorption to PAC. On the other hand, for the other PFAS, there was an important removal of these compounds in experimental phase C, where a higher concentration of suspended solids was available in the bioreactor, and also in phase C, where PAC was added in the bioreactor. We also observed that the addition of PAC in the bioreactor resulted also to a decrease on the ecotoxicity of the final effluent. We conducted two experiments, ecotoxicity assays, a germination test in order to check the phytotoxicity, and a Daphnia magna test in order to examine the ecotoxicity of the final effluent. To summarize, we could say that the coupling of the pretreatment processes with anaerobic digestion or GAC addition and voltage application in the anaerobic digester enhances biogas production. The operation of this pilot system indicates that substantial PFAS reduction is possible with a treatment rate of anaerobic digestion and hydrothermal carbonization, while the hydrochar liquid is heavily contaminated, mainly with soluble COD and ammonia nitrogen. Some traces of some PFAS are also found, and for this reason it is required further treatment. Many questions, of course, have been arising after finishing our experiments. I could say two basic questions. The first has to do with the fate of PFAS, the possible release of PFAS in the gas phase after hydrothermal carbonization. In our lab experiments, we applied some mass balances there, and we saw that a percentage lower than 1% was found in the gas phase. But in any case, it is something that is not known at the moment. Even in the literature, there are no many results for different PFAS and for their concentration levels in the gas. And also, there is a question about the fate of PFAS when the hydrochar is disposed to the soil. So these were my slides. Thank you for your attention, and I can reply to your questions.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.